Okay, in this video I'm going to talk about how to obtain binary and Probit regression results using R. Most of the demonstration is going to center on binary logistic regression, but I will show you also later on in the video how to obtain Probit results with just a couple of minor modifications. The PowerPoint that you see right here is available for download underneath the video description, so be sure to check that out. And so we'll start off just with a couple of preliminaries on how to obtain the data and obtain the relevant packages. So the packages that I'm using in this particular video are the FMSB package right here, which is going to be used for computing a Nagelkerke pseudo R square value. I'm going to be using the information value package right here, with the I and the V both in caps, and this is going to be used in order to compute a confusion matrix and evaluate specificity and sensitivity. And then we're going to be using the reg helper package in order to obtain basically partially standardized regression coefficients. The data can be downloaded from this link right here, and I actually have the data under my downloads folder, so I will open it up from there, and then we'll start looking at the data. So what I'm going to do though is I'm going to create a data object using the read table function in order to import the data from a CSV file into R. So just again note that the data is in a CSV format. So I'm going to open up R right here, and the first thing that I need to do is to point the program to the folder containing my data set. So it's under the downloads folder. So I'm going to just click on File, go to Change Directory, and then I'm going to highlight Downloads right here and click on OK. If you are downloading or if you are working with the data set in a different folder, you'll need to point R to that folder instead. So now what I'm going to do is I'm going to just paste in that syntax from the slide. And just note, I'm going to largely do a lot of copying and pasting in this video just to keep the video hopefully reasonably short on time. So you can see right here I've got my data. That's the data object that's containing the data. And so this is a data frame with our variables. So I am now going to just type in my data, and we'll just take a look at it. You'll see that we have 45 cases, and the scenario is basically where we're kind of pretending to be counseling researchers looking at predictors of the likelihood of early termination from counseling. So the terminate variable is our binary outcome variable. It's coded 1 for early termination, 0 for non-early termination. And then we have 3 predictors, 2 of which are being treated as continuous. The first one is avoidance of disclosure, and the second one is symptom severity. And then we have sex, which is a dummy coded variable, coded 0 for male and 1 for female. So now let's run our analysis. So we're going to start off, I'm going to run 2 logistic regression models and create data objects that contain those results. The first one is going to be a null or intercept only model, and then the second one is going to be a full model containing my full slate of predictors. So the syntax for both of these, this is the data object name that's going to contain the results. You can see that I have GLM right here. So in both of these we have the GLM. You'll notice that next we have the outcome variable terminate followed by a tilde sign. So for both of these. Now up here we have tilde1 right here, and here we have down below we have tilde followed by the names of each of our independent variables that are going to be included in our model. These are the names from the data frame, and then they're separated by plus signs. So the first one is telling us, or telling R, that we're going to be creating an intercept only model. The second model is going to be basically our full model containing our predictors. Next, you can see that we have we state data equals and then the name of our data frame. So data equals name of data frame, family equals binomial next, and then we have link equals and inside quotation marks logit, then followed up by our in parentheses right here. So I'm going to start off with the null model. I'm just going to copy this and paste it into R. And we can take a look at it using the summary function. So I'm going to type in summary BLR NM, and there you go. And you can see that this is an intercept only model. The only coefficient that appears is the intercept right here. So the second model was our full model, and so I'm just going to copy this and paste this in as well. And if we use our summary function, we're going to type in BLRFM, and there you go. And so looking at this, you can see that we have all of our predictors that are included. So these are our coefficients, standard errors, z-values, and p-values. And so right here you can see that, well, first off, let's just keep in mind our dependent variable is coded 0 for not terminating early, 1 for terminating early. So if we have a positive coefficient like we have right here, that would indicate that with higher scores on the predictor variable, there's an increased likelihood of terminating early. If we have a negative coefficient like we see right here, then higher scores on the predictor are associated with lower likelihood of terminating early. So you can see right here that avoidance of disclosure, there's a positive coefficient and significant. That indicates that individuals scoring higher on avoidance of disclosure were more likely to terminate early than those individuals scoring lower on avoidance of disclosure. Symptom severity, given the negative coefficient, and it was significant, that would indicate that individuals with higher symptoms or greater symptom severity were less likely to terminate early. Then when we look at sex, you can see we have a negative coefficient, basically indicating, again, males were coded 0, females were coded 1. So that indicates that females were less likely to terminate early than males, but that predictor was not significant in the model. So there you go. So next up, we can generate confidence intervals using this function right here, confint dot default, and then inside the parenthesis we have the name of the data object containing our GLM results from the full model. So I'm going to copy this and paste this in right here. And so now you can see we have 95% confidence intervals. If we want odds ratios associated with our predictors, we can type in EXP, and then we've got inside parenthesis COEF, and inside another parenthesis the name of our data object with our GLM results. So in this case, we have the odds ratios associated with each of our predictor variables. And then finally, if we want to compare our full model to the null model, and basically we can ask the question, does our full model represent a significant improvement in fit over the null model with no predictors? We can use the ANOVA function that we have right here. Just keep in mind that there are packages out there where the ANOVA function, there's a capital A at the start, and so that would be the wrong function to use in this particular case. So we're trying to compare these two models right here, and so we need little a NOVA, and then you can see that we have the name of our data object for the null model, and then for the full model right here, and then followed by the comma, then we have test equals, and inside quotation marks, capital C, H, then HISQ, in quotation marks, in parentheses. So this is basically going to be a likelihood ratio chi-square value, or test, excuse me. So you can see right here that there's our function, and so our chi-square likelihood ratio value is 28.552. You can see the degrees of freedom right here, and then the p-value for our test. So you can see that it's statistically significant, indicating that we have our full model represents a significant improvement in fit over the null model. So next up, let's say that we want to obtain standardized regression coefficients. So we're actually obtaining partially standardized coefficients, and so this would be analogous to essentially taking our predictor variables and z-scoring them and then entering them as predictors in our logistic regression model. So, but we can use the regression helper model, regression helper package with the beta function associated with it in order to obtain these coefficients. So I'm going to go under R right here, and I'm going to type in library, and then inside parenthesis reg helper. So now we're ready to go, and I'm going to type in beta, and then I'm going to type in the name of our data object from containing the GLM results from our full model. So BLR, then FM right here. And so now you can see that in our estimates column right here, these are all standardized, basically partially standardized regression slopes. So you can see right here, you've got avoidance of disclosure .z, symptom severity .z, and sex.z. So all of those are we can use these coefficients to make comparative judgments about which predictors are contributing more or less in the model. So you can see avoidance of disclosure has the largest coefficient at 1.99. Symptom severity has the next largest coefficient at negative 1.5598. And then sex has the weakest coefficient at negative 0.6779. So just taking the absolute values of these coefficients, we can rank order them in terms of their relative contributions to the model. Now, if we want McFadden pseudo R-square, we can compute that using this formula right here. So it's 1 minus the log likelihood from the full model divided by the log likelihood for the null model. So we're just taking 1 minus the ratio of the log likelihoods for the full to the null models. So basically, this is the syntax that I'm going to use in this particular case, and I'll walk you through it. So you can see right here that I've typed in 1 minus, and then you'll see in lowercase log, then you have a capital L, and then lowercase ik right there. So that's going to be the same as what we have right here, and then inside the parenthesis we have the data object name for our full model, and then the data object name for the null model. So the McFadden pseudo R-square value is 0.46, which you see right here. Next up, to obtain Nagelkerke's pseudo R-square, if you want that, we can type in library FMSB. So I'll do that. And next we can type in Nagelkerke, and then capital R2, and then we'll type in the name of our data object again. So BLRFM, and there you go. So now you can see the Nagelkerke pseudo R-square value is roughly 0.629 that you see right there. So next up, if we want to obtain sensitivity and specificity along with the confusion matrix, we can do this in the following way. So first, step one, we need to create a data object that contains the predicted probabilities of a given case falling into the target group, which is the terminate early group. So this right here is the name of our data object, and you can see that we're using the predict function right here, followed by the name associated with our full model, the data object containing the results from the full model. Then you see my data following, which is our data frame. Then you see comma, then type equals, and then quotation marks, response, end quotes, and then in parentheses. So the first thing I'm going to do is I'm just going to put this into R right here. And if you want to look at the data object for the predicted probabilities, you can just type in predicted, and there they are. So these are the predicted probabilities of falling into the target group based on the model. That's for each of the individual cases. So next up, we will use the information value package. So I'm going to call that up using the library function. So library and then information value, enter. And so it's ready to go. So the next thing we'll do is we'll create a confusion matrix, and the function is confusion matrix with a capital M in there, by the way. Inside the parenthesis we have my data, that's the data frame name, followed by a $sign, followed by the outcome variable, which is our binary outcome terminate. Then we have comma, then predicted, and then we have a threshold value for essentially creating our categorizations. So you can see right here that if I copy this and paste this in right here, again, you can type this in yourself later, but you'll see that we have our confusion matrix, And we have essentially the columns are representing the actual outcomes. So 0 reflects those individuals who did not terminate early. 1 is reflecting those individuals who did terminate early. And then the rows are reflecting the predicted outcomes. So basically, row 0, these are individuals that were predicted not to terminate early, and the ones are reflecting predicted cases that were are the cases that were predicted to terminate early. So you can see that we had essentially 23 individuals that were correctly predicted by the model to not terminate early, and 15 individuals that were correctly predicted by the model to terminate early. And basically, if we take, if we think of these individuals as the non-terminating early individuals, we have 23 of the individuals who did not terminate early were predicted by the model. So if we take basically 23 divided by the sum of essentially these two cells right here, that would, which is 25, that would give us the proportion of individuals correctly predicted not to terminate early. And then by the same token, if we take this 15 right here for this cell and divide it by the sum of these two cells right here, then that would get us the proportion of the cases that were correctly predicted to terminate early. So that's where you get into talking about sensitivity and specificity. So let's kind of look at this a little bit more closely. So specificity, I've kind of laid it out in my PowerPoint right here, but specificity is just basically computed by taking A and dividing it by the sum of A and C right here. And so you can see that if we take 23 divided by 25, that gets us 0.92. And so that's telling us that 92% of those cases that fell in group 0 were correctly predicted by the model to fall into group 0. And so that's our specificity right there. And sensitivity is basically taking a ratio of cell D to the sum of cells B and D right there. And so you can see it's 15 divided by 20, and that gets us 0.75. So 75% of those cases falling into group 1, which is the termination group, were correctly predicted by the model to do so. So to obtain the sensitivity and specificity for the model, you'll notice that really we're leaving this part of our previous syntax intact. The only thing that we're going to change is the function. So you'll see down here it says specificity and then everything else. So I'm just going to copy this and paste it in. So the specificity for our model was 0.92. So again, basically what that tells us is that 92% of those cases that did not actually terminate were predicted not to terminate. Whereas when we look at sensitivity, and so I'm using the sensitivity function, we see that 75% of the individuals who actually did terminate early were predicted to terminate early by the model. So if we want overall classification error and accuracy rates, we still leave everything else exactly the same as what we've had before, but we can use the misclass error function. So you'll see that the C and the E in this are in caps. So I'll copy this and paste it in, and you can see that what this tells us is that roughly 16% of our cases were incorrectly classified based on the model. And if we want the overall classification accuracy, we can just basically type in 1 minus and then use that same function, and you can see that now we get 0.84. So 84% of our cases were correctly classified based on the model. Now, in terms of Probit regression, as I said earlier, it doesn't involve a whole lot different from what we've already done. The main difference is then that we're going to be using the Probit link function. So you can see right here, I'm just creating a null model, a Probit, a data object containing the results from the null model, and Probit, basically a data object containing results from the full model. So everything else is exactly the same except for the name of my data object and the link function. So I'm going to actually start off with the null model. I'm going to copy that and paste it in. And you can see one of the kind of frustrating things sometimes is that if you create syntax external to R and then you try to paste it in, sometimes you'll get an error. The error here comes from the quotation marks being italics. So what I'm going to do is I'm going to re-highlight this, and I will paste that in right here, and I will say link equals and then quotation marks Probit in quotes and then in parentheses, 2 of those right there. And then for the next demonstration, we'll just do the same thing. I'm just going to copy this portion right here and go with it. So we'll say link equals and then quotation marks Probit in quotes in parenthesis here. And there you go. So next up, if we want the summary from the full model, we'll just use the summary function. And so now you can see we have our regression coefficients, and really the results are not telling us that much different from what we had before with our binary logistic regression. If we want confidence intervals, we can still use this function right here. So it's CONFINT dot default, and then inside the parenthesis the name of the data object containing the results from the full model. And we can also get our odds ratios by using the EXP and COEF functions. So you can see right here, now I've got odds ratios associated with the predictors. And then finally, we can use our ANOVA function, as I talked about before, and compare the null results versus the full model results, and using essentially the likelihood ratio chi-square test. So there it is, and you can see right here we have our comparison, our chi-square value, degrees of freedom, and then the significance level right there. So at any rate, one other thing, if you want to use the beta function associated with the regression helper package, you can still do that as well. So since I actually still have the package in operation, what I'll do is I'll just type in beta, and then we'll type in the name of our data object, so Probit, then FM right here, and there you go. So now we have the partially standardized coefficients. So that pretty well concludes this demonstration.